So here again is another overview on inverses. Probably similar to the last video in many ways, but again, let's see what happens here. The key for an inverse function or an inverse relation is that the idea of undoing. And as I told you guys, gave the analogy, suppose I have this function. The function is I'm getting to a point where my socks are on and my shoes are on. There's a particular order normally. I put my socks on first, and then I put my shoes on. If I want to undo that process, I reverse the order and I reverse the operation. So I put my socks on first, and then I put my shoes on. To undo that, my shoes come off, then my socks come off. So continuing with this idea of undoing, if I have a function, the tripling function, g of x equals 3x, what would undo that? And our notation, notice, is very confusing. This -1 up here, written between the function rule and the parentheses with our input, indicates that this is read as g inverse of x. G inverse of x. What would undo our tripling rule? Well, multiplying by 1/3 would undo our tripling rule. That's the equivalent of dividing by 3. Note, if I want to actually write the reciprocal of a function, for example, if I want to take that some function, let's say we have f of x equals the square root of x, and I actually want to take its reciprocal, I would write f of x, and then the whole thing in parentheses I would reciprocate. That would be 1 over root x. So if we've got a function which is the squaring function, what would undo that? The inverse would be the square rooting function. And note, when I take a square root of a number, of a permissible number, I take a positive or negative. And note, for this rule, supposedly this function, there would be 2 outputs for an input. And again, if we think about it, our function, our squaring function looks like this. Our plus or minus square root function looks like this. And indeed, the squaring function, with no restrictions on its domain, does not have an inverse. I would have to call this the inverse relation of the function h of x equals x squared. And I would say again that this function h does not have an inverse function. It only has an inverse relation. So again, to find an inverse of something where you can look and see order of operations and what you're doing to an input, what I'm doing here is I'm squaring first, and then I am multiplying by 3, and then I am adding 7. What would undo that? Undoing that, opposite order, opposite operation, subtract 7, divide by 3, and then square root. Now again, I'm not going to get a function here because when I take a square root, I must put in a plus or minus. So subtract 7, divide by 3, and take square root, and in this case, plus or minus the square root of x minus 7 over 3. So, schematically here, I take an input x, I apply f to it, I apply my rule to it, I get an output. If I want to go back to where I started from, my output now, f of x, needs to head back to x, go back to where it came from, and I apply the inverse rule to it. So note my ordered pairs for the function f. Input x, output f of x. And then, if I'm going to undo f, my outputs for f of x outputs, which are now inputs for the inverse, I apply that inverse rule to them and I get sent back to x. So on my inverse function graph, or inverse relation graph, I will have f of x comma x. So what's the relationship you notice between these two ordered pairs? Clearly x and y have switched. And indeed, for inverse functions or relations, if I switch x and y, I get an inverse relationship. Now again, you've seen in a couple times, and we'll keep hammering at this idea, that why do inverse functions, why are they symmetrical but the line y equals x? Well, what we just looked at from the previous slide, we noted that if we have a point a, b on a function, we have the point BA on the inverse. And if I then go ahead and connect those 2 points, any pairs of points AB with their counterpart BA on the function its inverse, and then look at a perpendicular bisector for the segment connecting a point on the function and its counterpart on the inverse, let's see if we can get what the equation of that line is. Now the slope of that line is going to be the negative reciprocal of the slope of the line connecting AB and BA. That line has a slope of -1, as you can see, so its negative reciprocal will be +1. So the slope of the perpendicular bisector connecting a point on a function and its corresponding point on the inverse has a slope of 1. Now, in addition to having a slope of 1, that line also passes through, the midpoint of that line is going to be at a plus b over 2, a plus b over 2, so it's going to pass through a point where the x and y coordinates are the same. What would be the equation of a line in this first quadrant with a slope of 1 that passes through points like DD or EE or FF or a plus b over 2, a plus b over 2? Clearly that's the line that bisects quadrants 1 and 3, or the line y equals x. And so if that line y equals x is the perpendicular bisector of every pair of points on a function and its inverse, then that line is going to be a line of symmetry for a function and its inverse, because that's our definition of what a line of symmetry is. Connect 2 corresponding points on your graphs, and if that line is the perpendicular bisector of the segment connecting those 2 points, then that line is a line of symmetry. Now I can go ahead and sketch, if I'm good at sketching and at seeing things, I can go ahead and sketch where my inverse will go, inverse relation or inverse function, based on my graph and on my line of symmetry y equals x. So if I look at this here and I want to sketch in something that's going to look like it has symmetry with the line y equals x, it would look something like that. Again, if I were to fold over the line y equals x, the function is going to fold over onto its inverse and vice versa. Once again, if we look at a parabola, f of x equals 3x squared plus 1, it's a parabola that opens up. It's a vertical stretch of x squared moved up 1. It's going to look something like this. If I look at symmetry over the line y equals x, I know my inverse is going to look something like this. I know my inverse by the vertical line test. Then this inverse relation is not a function. I would say f does not have an inverse function. F only has an inverse relation. And we are primarily interested in whether or not a function has an inverse function or not. So our terminology would actually be f does not have an inverse because the inverse relation does not pass the vertical line test. And if a function doesn't have an inverse function, we're going to say the function does not have an inverse. At least our textbook is going to use that model. So, and again, if I go ahead and do this algebraically, the other way that you've learned in the past on how to find the inverse of a function is to go ahead, instead of doing it as I've shown you by the undoing principle, algorithmic method is to go ahead and use y notation, so let f of x equals y, switch x and y, and then algebraically solve for y. And note when I solve for y here in this step, I've got to take a square root, so I've got to put a plus or minus in, and that's going to give me 2 outputs, 2 different outputs for 1 input. And so we say that f does not have an inverse that is a function. F only has an inverse relation. And finally, one more example of, again, using the undoing principle for finding an inverse. Let's suppose we have some function, nasty looking function like this, and we want to find its inverse. We note that our order here, our rule that gets us our output, is to multiply by 4 first, then we subtract 7, we cube root, we divide by 2. Reverse and change to the opposite operation. I'm going to multiply by 2. Then I'm going to cube. Then I'm going to add 7, divide by 4. And I can write that down. And so therefore my inverse is 2x cubed plus 7 over 4. If I want to go ahead and simplify that, lo and behold, 8x cubed plus 7 over 4.